Let us move on to analysis of flow measuring devices. The first one is a Venturi meter. So a Venturi meter is basically a short pipe which consists of two conical sections. So this is one end of a pipe and this is another end of a pipe, and in between these two pipes we attach a piece which has two conical sections. So the first part is the converging section, and the converging section has a larger converging angle than the diverging section. The diverging section, the angle is quite mild, and the reason for keeping the angle quite mild is to avoid any kind of flow separation. If there is flow separation, meaning the incoming section is something like this and the outgoing section is also something like that, then a streamline will try to be concentrated in this region rather than spreading out into the other region. And if there is a net flow in this direction, there will be a circulation zone like this. So these circulation zones essentially are eddies which extract a certain energy from the incoming flow in order to sustain their vorticity. So we want to avoid flow separation in order to prevent any non-idealities in the flow. Remember that any non-ideality in the flow amounts to deviation from the Bernoulli equation, because the Bernoulli equation is essentially a statement of the conservation of energy. So if this is the direction of the flow, we can apply Bernoulli equation between any 2 points. Well, rather than saying any 2 points, we'll apply it between a point upstream of the throat and a point at the throat. So the assumptions are still the same. It's incompressible, inviscid, and in this case it's a steady flow as well. Well, one may ask whether this inviscid assumption is true for flow through pipes. And in fact, if the velocity is quite large, the viscous effects will be confined to regions near the wall. So very close to the wall, the viscous effects will not be negligible. In fact, this we will study in larger detail in boundary layer theory. But it is sufficient to say for now that the core of the flow can be considered to be inviscid when the Reynolds number is quite large. Now in this case, we can apply Bernoulli theorem along a streamline which goes straight like this across stations 1 and 2. So let us see what we obtain. So we will have P1 plus, or rather let us write it in the terms of head, P1 by rho g plus V1 square upon 2g plus Z1 is equal to P2 upon rho g plus V2 square upon 2g plus Z2. And therefore we can write V2 square minus V1 square upon 2g is equal to P1 minus P2 upon rho g plus Z1 minus Z2. Or we can group certain terms. So we can make a group like this: P1 upon rho g plus Z1 minus of P2 upon rho g plus Z2. This particular combination of terms, P1 upon rho g plus Z1, is called as the piezometric head, and we denote it as H star. So this particular set of terms, it essentially boils down to H1 star minus H2 star. So far we have V2 square minus V1 square upon 2g is equal to H1 star minus H2 star. So a piezometric head is something which will be measured by a piezometer. So a piezometer is able to separate out the dynamic fluxes or the dynamic pressure. So this particular contribution, half rho v square, that is called as the dynamic pressure. And the piezometer is not able to measure the dynamic pressure, but it is able to measure the combination of P plus rho g z. Hence, that particular head is also called as a piezometric head. So, we can make use of the continuity equation between stations 1 and 2 to write A1 V1 is equal to A2 V2. And this is true when the flow is steady and the density remains constant across the two cross sections. So now we can essentially write V1 is equal to V2 times A2 upon A1. So we can substitute this over here to write down V2 square upon 2G 1 minus V1 square upon V2 square is equal to H1 star minus H2 star. And this implies that V2 is equal to 2G H1 star minus H2 star divided by 1 minus A2 upon A1 whole squared. And because it's squared, we have to take a square root of this entire thing. So this gives us an expression for the velocity in terms of the difference in the piezometric height between points 1 and 2. And this equation clearly means that the velocity that we will get at the throat, this particular point is called as the throat. So the velocity at the throat is sort of driven by the difference in the piezometric head. So proceeding further, what if we could measure the difference in the piezometric head? So an analog way, nowadays there are various digital ways of doing it, but an analog way of achieving that is by means of manometric tubes connected to various side ports. So let me draw, or let me just copy this Venturi and let me draw it in a random orientation. Alright, so this is point 1, this is point 2. So we make a hole in the pipe, very small hole, and we connect a manometer tube between these 2 points. Okay, you get the point. So this manometer is filled with a manometric fluid, which I'm marking by a green hatch. Okay, so first of all, because of the differences in the piezometric pressures at point 1 and point 2, there will be a difference in height, obviously. So now let us take this as the reference location. Considering this as the reference location, we can sort of write down a balance in the static conditions at this point. So if I call this point at A and if I call this point at B, the fact that the manometer fluid in equilibrium, in static equilibrium, takes this particular shape means that the pressure at point A and pressure at point B will be equal. This height, let me call it as Z1, this particular height, let me call it as Z2 from the reference location. This height, let me call it as H naught. So equating PA and PB under static conditions, we can write P1 plus rho G. So now this entire section is filled with the working fluid, whatever fluid is moving through the venturi. So this is simply rho. This is going to be Z1 minus H naught, and this will be equal to PB. So PB is equal to P2 plus rho G times this height. So let me call this particular height as capital H. So this particular height, it becomes Z2 minus capital H minus H naught. So Z2 is this entire height minus of H plus H naught. So H plus H naught is essentially this height. So this is H naught. So that gives us this particular height. So this particular height is filled with the same working fluid which has a density of rho plus the manometric fluid. So the manometric fluid has a height equal to capital H. So this will be rho m times G times H. And thus we have the manometric conditions of hydrostatics PA equal to PB. And this gives us P1 plus rho G Z1 minus P2 plus rho G Z2. Essentially, I'm taking combinations of these terms and these terms, and rest of it will be rho G minus H naught plus rho G H naught plus rho M G H. And so this minus rho G H naught and rho G H naught cancels out. So we have minus rho G capital H plus rho M G H. And this simplifies to rho M minus rho times GH. And therefore P1 plus rho G Z1 minus of P2 plus rho G Z2 is equal to, so if I take rho common, so it becomes rho G rho M upon rho minus 1 times H. If I divide everything by rho G to convert it from pressure to head, I obtain P1 upon rho G plus Z1 minus P2 upon rho G plus Z2 is equal to rho M upon rho minus 1 times H. So this actually gives us the difference in the piezometric pressure. So this is H1 star minus H2 star, and it is simply equal to rho M upon rho minus 1 times H. So now we can substitute this particular expression over into the expression for the velocity. So this becomes V2 equal to square root of 2g, and this piezometric height difference is equal to rho m upon rho minus 1 times the difference in the manometric limbs. This is A2 upon A1 whole square. So where h is the difference in manometric height in two limbs. Essentially, it's a differential manometric measurement because it's actually measuring the difference in the pressure between 2 points. Hence, it is often called as a differential measurement. Okay. So interestingly, this expression for the velocity in terms of the difference in the manometric height between the two limbs is independent of the orientation of the tube. Nowhere in picture came what this particular angle is, and that's that information is encoded inside the difference in heights. Actually, it does not depend on the angle because the velocity depends in the difference in the piezometric pressure and not just the pressure or not just the hydrostatic. So V2 finally comes out to be square root of 2g rho m upon rho minus 1 times h divided by square root of 1 minus a2 upon a1 whole square. So correspondingly, the volume flux is equal to V2 times A2, and you can multiply this entire term. So if I multiply it by A2, it is simply A2, and this becomes the volume flux. Now, in reality, the volume flux will not be equal to this quantity. In fact, it will be lower than this quantity, and it will be lower on account of losses due to friction. So Venturi meter usually does not have losses due to eddies, but the fact that viscosity is actually present in the problem does lead to a reduction in the energy as fluid goes from point 1 to point 2, and that reduction in energy reflects in the form of a loss in velocity. So the actual flow rate will actually be lower than the theoretical flow rate, and this particular ratio, the ratio of the actual flow rate by the theoretical flow rate, is called as the coefficient of discharge. It is called as CD. It is the coefficient of discharge. Okay, so if someone says what is the coefficient of discharge for a very well made manometer, for an ideal manometer, rather for an ideal Venturi meter, the coefficient of discharge will be equal to 1. For a very good quality but real Venturi meter, the coefficient of discharge will be something which ranges from 0.95 to something 0.98. So it means that whatever you measure as the actual flow rate, if you compare it with the theoretical calculations, there will be a certain reduction, and larger the Reynolds number, the better will be the coefficient of discharge, on account of the fact that at larger Reynolds numbers, the viscous boundary layers are more and more confined near the wall. However, for larger Reynolds number, you run into the risk of making the flow quite turbulent. And the moment the flow becomes turbulent, you sort of start losing energy to eddies. So we want to avoid that as well.